Hi guys, this is Siri, and in this video we're going to be talking about how we solve systems of equations using a technique called row reduction. We've talked about systems of equations in our previous videos, and we've talked about matrix notation and the augmented matrix, and so hopefully you're familiar now with how we represent a system of linear equations using a matrix, and how we just put the coefficients inside a matrix, and if we want, put the constants as the last column of our matrix as well. So let's start talking about row reduction. So row reduction is a technique that involves matrices, and you might be familiar with solving systems of linear equations using techniques like substitution and elimination. And in this video, we're going to be finding a way to do the same thing in a much more, faster way and much easier way. And this is essentially replacing a system with an equivalent system, and this is a term that we've covered in, I think, our first video. Equivalent systems are systems that have the same solution set. Okay, so it's like the equations. So when you solve a system of equations, you get a solution for your variables, right? Your x1, your x2, your x3. So x1 equals something, x2 equals another number, and x3 equals another number. And when you have two systems and your variables are equal to the same values, meaning the solutions are the same, meaning that when you substitute in these values for the variables, you get true statements, you get true equations. So we're replacing one system with an equivalent system that is easier to solve. And by easier, I mean very easy, that essentially that you literally get the values of your variables. So this might all be confusing to you because we haven't really seen an example yet, but the idea is that we are replacing a system. A system is just a linear system, which is just a collection of linear equations. Replacing a linear system, with an equivalent system. That is easier to solve. Very easy. Easier to solve. Okay. So, and this is going to be more systematic than just substitution, because in substitution you can substitute any variable, you can plug it into any equation, you can add any two equations and eliminate any variables, and you might have an idea of and a sense of what you're doing, but it's not as systematic. So let's find a systematic way of doing this. So the three operations that we're allowed to do in order to transform one system into an equivalent system that's easier to solve, when in that transformation, not a transformation, but when we're converting one system to another equivalent system, we have to take a series of steps, right? It's not, although they're equal, we need to show that they're equal and then arrive at a solution. And the operations that we take to get there are called elementary row operations. Okay, so they're called elementary row operations. Okay, So there are like 3 operations that we're allowed to do, and by doing these 3 operations, we're not changing the solution set. Okay, that's the idea, because they're equivalent systems. The system that you have at the beginning and the system that you have at the end are equivalent. They have the same solutions, so therefore these steps do not change that. They do not change the solution set, so they're safe to do. Okay, so the first one that we're going to be talking about is replacement. So we're going to talk about replacing one row with or like by the sum of that row that we're talking about, by the sum of itself and a multiple of another row. Okay, so for example, if we have like going back to the example that we were talking about like yesterday, you know, when you have like x1 minus 2x2 plus x3 equals 0, 2x2 minus 8x3 equals 8, and 5x1 minus 5x3 equals 10, you know, I'm not saying that we would actually do this replacement, but something that you can do is take this row and replace it. So essentially replace this 1, -2, 1, 0 with something else. So with like so we're replacing this 1, -2, 1, 0 with like 2 times the third row, the third equation. So yeah, that's 1. And 2 is you know, interchanging 2 rows, so like swapping rows. So you can switch out, we can like swap the positions of the rows, so we can make the 0, 2, -8, and 8 as the first row, and push the 1, -2, 1, 0 to the second row or something like that. We wouldn't actually do that, but I'm just saying that we can. It doesn't change the solution set, and we would still arrive at an equivalent system. That's what I'm saying. It's not necessarily the easiest, but we will talk about how we find the easiest solution, easiest system to solve. Okay, what I'm just describing here is how these work, and how we would actually implement them. Okay, and just like what they mean. So the last elementary row operation that we can do is scale. Is to scale a row. So scaling a row is just multiplying that row by a constant, like this, right? Multiplying it by 2 or multiplying it by -1. The only thing that we need to make sure of is that it's a non-zero constant. So we can't, multiply a row by 0, because then we don't know what's, then it doesn't even matter what the original row was. Like any row multiplied by 0 is 0. So that just makes things confusing. Things don't work out at the end. So we can scale by a non-zero constant. Okay, and what I've been telling you is that these row operations don't change the solution set. So why am I saying that? Well, 2 and 3 I can explain easily, but number 1, we're not gonna. It's a pretty straightforward proof, but I'm not gonna go into it. You just have to take my word for that, or search up a proof. But the number 2 and 3 are pretty easy to understand, because rows just represent equations, right? They're not like just like random numbers, right? They represent equations. And just think about it. When you have x1 minus x2 plus x3, and you have 2x2 minus 8x3 equals 8, and 5x1 minus 8x3 equals 10, it doesn't matter whether you consider this the first equation, or this the second equation, or this the third equation, right? It's just a collection of 3 equations. The order of the equation doesn't matter. It doesn't even have an order, right? Like, what do you mean order of equation? No, like, it's just a collection of equations, and it doesn't matter whether we write this one first, or that one first, or number 2 first. It doesn't matter. It's just the same collection of equations, and it's going to have the same solution set, which is why you can swap rows. And the reason why you can scale is, like, forget about equations. Like, when you don't forget about equations. Forget about linear equations. When you just have like 4 equals 2 times 2, right? Or maybe like 14 equals 2 times 3. Wait. 2 times 3, which is 6 plus 8, right? So when you just multiply one side by 2 and the other side by 2, right? This is 14, right? 14 times 2 equals 14 times 2. Same with equations. We have 2 things equal to each other. You're multiplying them by the same number. They're obviously going to be the same, right? As long as it's non-zero. Well, not as long as it's non-zero, but it's a bit ambiguous when it's 0. But what I'm saying is, when you have a non-zero constant and you multiply 2 sides of an equal sign by the same number, it's obviously going to be the same, right? So that's why you can do numbers 2 and 3. Number 1, like I said, it's still a straightforward proof, but I would recommend looking through a textbook for that, because I'm not going to go through that now. Okay, so we do have steps for row reduction, which I can go through now, but I think it's there are 5 or 6 steps, which I'm going to go through it in another video, so you can look forward to that. Hopefully you understand that there are 3 elementary row operations, and the actual algorithm, the row reduction algorithm, we'll go through in our next video. Okay, so you can look forward to that. Thank you.